We go on with the mathematics of artificial intelligence by looking at why similar words live near each other. Okay, so here we'll be looking at things about vector spaces. We've seen a bit of that in the previous videos. Then we'll talk about similarity, word embedding, semantic search, and retrieval systems. And by the end of this lesson, you'll be able to understand why a vector space is. I mean, what a vector space is, why words can be represented as vectors, why similar words end up near each other. That's the crux of this video. Then how similarity is measured mathematically, how embeddings are learned, how semantic search works, and how retrieval systems use embeddings as far as artificial intelligence is concerned. So let's go ahead and talk about the core idea. So first off, humans naturally understand that cat and kitten are related, of course. Then doctor and physician are similar. Car and automobile are similar too. Computers do not understand meaning directly, unlike humans. So to make language understandable to machines, we convert words into vectors. Instead of storing cat, dog, and car, then we represent them as something like 0.21 minus 0.55, 0.89, and so on. So we represent each word in different dimensions. So each word becomes a point in a high dimensional space. And the remarkable observation is that words with similar meanings tend to occupy nearby locations in this space, right? So the idea forms the foundation of modern natural language processing. Now you see that here, for the first dimension, right? Cat is 0.1, dog is 0.19, but car is far away at 0 minus 0.71. So because cat and dog are closer together. On the other hand, second dimension, you have minus 0.55 minus 0.52, while this is 0.34, totally far away. Then 0.89. So by doing this kind of representation alone, we already put the words close by themselves. Now, the next question is, okay, so the core idea, like we saw already, is the fact is that um, humans understand language, computers do not understand language. So to make computers or machines, as we can, in the general sense, to understand human language, we need to turn human words into numbers, into vectors that can be understood by machines. So next, what is a vector space? A vector space is a mathematical space where objects are represented by vectors. So like this example shown here already. So for each word now, we have a we have each one represented by a high dimensional vector space. So a vector space is a mathematical space where objects are represented by vectors. For example, suppose we describe animals using two features. Say cat, for friendliness, we say 7. For size, we say 4. Dog, friendliness is higher than cat, that's 9. And in size, 6. For tiger, of course, a tiger is hardly as friendly as a cat and a dog. So it will be far away from these two in friendliness. And in size, of course, it's bigger than both of them. So a tiger is maybe size 10. So the corresponding vectors can then be something like this. For cat, we have 7, 4. Friendliness is one dimension, size is another dimension. So for cat, we have 7 by 4, dog 9 by 6, tiger 3 by 10. So these vectors become points in a geometric space. So you see, we are converting human words, human language into machine language by using vector spaces. Now, the vectors become points in the geometric space. Nearby points represent similar objects. So you can see cat and dog are closer together if you look at the distance between them, even you know, at first sight. The faraway points represent different objects. So you see, this whole thing tells you that cat and dog are closer together than cat and dog are close to tiger. Then let's go on and talk about from features to meaning. So in traditional machine learning, features were manually engineered, right? For example, friendliness, size, speed, and intelligence. However, language is too complex for manual feature design. So modern embedding methods automatically learn useful features from large text collections. For example, now you can have king to be 0.82 minus 0.11, 0.47. Queen is 0.79 minus 0.09, 0.51, and so on. Man is 0.71. Woman is 0.69. So, king and queen are related somewhat. Of course, king and man, I mean, a king is closer to a queen than a king maybe closer to just ordinary man. So that kind of thinking, right? So the dimensions do not correspond to human interpretable concept. Instead, they encode statistical patterns learned from language, right? So next thing is why similar words become neighbors, which is why what this video is about. So the main idea comes from the distributional hypothesis that words that occur in similar context tend to have similar meanings. So consider that the cat sat on the mat, for instance, and the kitten sat on the mat. So the words cat and kitten appear in nearly identical contexts. So similarly, if you then say the doctor treated the patient, the physician treated the patient, the words doctor and physician appear in nearly identical context because the surrounding words are similar, the length vectors become similar. So as a result, now we can say that doctor is approximately physician, cat is approximately kitten, and car is approximately automobile in vector space like that. So that's what it is that why we have it that similar words become neighbors because they are used in similar contexts. So let's talk about context creating how context creates geometry. In the last video, we saw how AI converts words into coordinates. So it's about the same idea. So imagine a giant word context matrix, for instance, and rows represent words and columns represent the contexts. For instance, you have cat. So cat is an animal, 500 points, pet 700 points, road 0, hospital 0, patient 0. Has nothing to do with all of this. Dog is an animal, 600, pet 800. It's more animal, it's more pets than cats, so to speak. Maybe more people love dog as pets than cats, maybe. Then road, hospital, and patient, totally unconcerned. Then you have car, not an animal, not a pet, but it can walk on the road. Not no hospital, no patient context. For doctor, no animal, no pet, no road. But then you have them in hospitals, you have them attending to patients, and physician is about the same thing. So each row then becomes a vector, in those contexts now. For example, so you can then have cat to be 500, 700, 000, and dog is 600, 800, 000. Notice that cat and dog have similar patterns, okay? Similar patterns in that they score points in the same context of being animal and pets, while doctor and physician score points in the same context of being in hospitals and attending to patients. So therefore, they occupy nearby regions in the vector space, right? So we then go ahead to talk about measuring similarity, which I think we've made mention of that a little bit in previous videos. To determine whether two vectors are similar, we need a similarity measure. So we need something that talks about the similarity between them. So two common approaches are Euclidean distance. That's the distance we know x, the normal x, y, x1, y1, x2, y2 kind of distance. And then we have cosine similarity, which is really interesting, which is really important. Interestingly, we are going to also still consider cosine similarity in the next video. So now talking about Euclidean distance here, right? Euclidean distance measures straight line distance between 2 points. So if you check the my playlist on coordinate geometry, so that's what Euclidean distance is all about. I guess I want to show that a little bit. Okay. Um, let me see that. Mm, okay, I need a notebook. OneNote, yeah, OneNote. So the basic idea of Euclidean distance is this that you have this, and then you have a point here, you have a point here, call this x1, y1, and you call this x2, y2. Can even have more points, but let's just have this. So you want to get this distance, right? And we know the way to get that is to project them onto a kind of triangle like this. So, and we know to get this distance, uh, so let's say this is r now. So we say r is equal to square root. Okay, or better still, we say that r squared, that's a hypotenuse right there, is equal to this distance. And this distance, if you look at it, this is the x-axis, right? So that'll be, this is x2 right here, this is x1 right here. So this distance is actually x2 minus x1. On the other hand, talking about this distance now, you have all of this to be, you have this now, this distance now to be y2 minus y1. So r squared is now x2 minus x1 squared plus y2 minus y1 squared. That's the Euclidean distance right there. So r squared. So r itself is just the square root of that. So x2 minus x1 all squared plus y2 minus y1 all squared. Something like that. So that's the idea of Euclidean distance right there. So when we come back here, we then see that so the summation of all those distances now. So distance between A and B is just AI minus BI all squared. So smaller distance means greater similarity. So once this distance is closer together, it means that they are very similar. That's for Euclidean distance right there. So example of Euclidean distance is what I just showed you there. So suppose A is 1, 2 and B is 2, 3. So distance between A and B is just 1 minus 2 squared plus 2 minus 3 squared. Or if you like 2 minus 1 squared plus 3 minus 2 squared, you get the same result, square root of 2, which is approximately 1.414. And then you can even do that using Python and you get 1.414 blah 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 if you need more decimal places. So that's one way to measure similarity, Euclidean distance. And then there's then cosine similarity. So for cosine similarity now, we have in natural language processing, direction is usually more important than magnitude. So direction is really more important than magnitude. Magnitude is what cosine similar Euclidean distance shows you, but here cosine similarity shows you direct magnitude and direction. So cosine similarity measures the angle between vectors, especially the angle, right? Cosine similarity measures the angle between vectors. So cosine similarity is measured as a dot b, the dot product of a and b divided by the product of the individual magnitudes of a and b, where a dot b now is the summation over I of ai bi. So the interpretation is this. So if you get one as cosine similarity, it means that the vectors are in the same direction. If it is zero, it means they're totally unrelated. If it's minus one, it means that the vectors are in opposite direction. So that shows you the similarity between words that have been embedded using these vector spaces. So look at this example, the same example like before, right? So here we had that 1, 2, 2, 3. So we are using the same. Okay, here we are using 1, 2, 2, 4. Okay, so up there we had 1.414 and all that. So let's see what we have here. So cosine, okay, they are not the same though. So I think we want to be a bit careful about that. So here you suppose A is 1, 2, B is 2, 4. So dot product is A dot B equals 1 times 2. That's 1 times 2 plus 2 times 4. That's 2 plus 8, which is 10. Magnitude of A is square root of 1 squared plus 2 squared, which is root 5. Magnitude of B is square root of 2 squared plus 4 squared, that's root 20. So cosine similarity tells you you have A dot B, which is 10 all over this 2. That's square root of 100, which is 10 in short. So 10 over 10 is 1. So the vectors point in exactly the same direction because the value is 1. Even if you had put 3 here, right? In fact, let me do 3 here so that so it's easy to compare, vector for vector, right? So 2, 3 there. So anywhere we see 4, we put 3. Um, so this is 1 squared, 2 squared, and 2. This is now 2, 3, 2, 3. So that's 2 plus 6. The 2 plus 6, which is 8 there. And then we come down here. So that's 2 squared plus 3 squared. 2 squared is 4, 3 squared is 9. 9 plus 4 is 13. 9 plus 4, that's 13. Then we come here and then we have, what's that now? We have 8 all over, this is 8 here. So we have root 5 multiplied by root 13. Something like this. So, the answer will have to change. So that's 8 over root 65. 8 over square root of 65. I mean, square root of 65 is almost 8 too, interestingly. So we have 8 divided by square roots of 65. So that's almost, oh no, square root of 65. This is given one already, but the actual thing will be different. 8 times square root of 65. So that's 0.9922, like that. Okay, so that's exactly what we have here. So when we come back here, right, you have what's different here now? Okay, this is 0.9922. Uh yeah, that's 0.9922 in short. That's 0.9922. So that way we are easily able to compare the same kind of vectors. So this is 0.9922 like that. So yeah, we have this. And this one is just giving us the magnitude of the distance. That's 1.414. That's what they are. But this talks about direction. And here, since 0.9922 is close to 1, it means that both vectors A and B are in the same direction. So they are so similar. So if I let me just come here and change this to 3, so we can see that 0.9922. So same like that. Now, the question is, between Euclidean distance and cosine similarity, which one is preferred? Obviously, as cosine similarity is preferred because of the direction. So why cosine similarity is preferred? Consider A is 1, 2, and B is 100, 200. Although B is much larger, both vectors point in exactly the same direction, because if you take the magnitude of this now, it's going to be so big and it will look like A and B are so far apart. But then if you look at it in terms of direction, you get that though they look far apart in magnitude, but the direction is in the same direction, because 100, 200 is just a multiple of B is a multiple of A, in short. So although B is much larger, both vectors point in exactly the same direction. So Euclidean distance considers them very far apart, but cosine similarity considers them identical. So for language application, semantic meaning is often encoded in direction rather than magnitude. So direction over magnitude, very important. Therefore, cosine similarity is widely used for embeddings, semantic search, document retrieval, and recommendation systems. Now, learning word embeddings. Now, how do we embed words? I think we've done a little bit about this also previously, but let's keep going. So the question is, who decides where words are placed? Who decides that? So the answer is the training algorithm. So you don't sit down. Imagine you have 1 million words in a document. So imagine you have to now assign values to it one after the other. So that doesn't work. That's where the place of the algorithm. So that's when you hear that a model is trained on data, this is the kind of thing that is happening in the background. So the answer is the training algorithm does decides where words are placed. So one famous approach is the word to vec. That's like word to vector. So the model repeatedly tries to predict neighboring words. For example, if you have the cat chased the mouse, so the input is so so for example, the cat chased the mouse. So if you put cat, so the targets are the chased and mouse, which are words that are close to cat to cat, right? So the model adjusts vectors so that words appearing in similar context become similar, right? Based on what that's learned from text, from documents, and all that. So after training, you discover that cat is close to dog, doctor is close to physician, and Paris is close to London somewhat because they behave similarly in language. Cat and dog are pets, they are animals. Doctor and physician are same words for people that do the same kind of job. Paris and London are capitals of countries, kind of. So because they behave similarly in language, so they are seen together as similar words when you train your model. So semantic structure then emerges. So embeddings learn relationships automatically. So a famous example is king minus man plus woman is approximately queen. So you have a king and take away man and you have woman, that's approximately a queen. So this suggests that semantic relationships correspond to directions in vector space. So, king and man are like in the same direction in a manner of speaking, but then, since you're talking in the context of a king, and if you add a woman to a king, you have a queen, kind of. So this suggests that semantic relations correspond to directions in vector space. So some directions encode concepts such as male, female, male to female, singular to plural, country to capital. Then meaning becomes geometry in that case. Now, let's see sentence embeddings. Words alone are often insufficient, right? So modern models generate embeddings for entire sentences. So, depending on the kind, whatever model you are using. So instead of embedding word by word, in fact, you can embed token by token or word by word, or even sentence by sentence. So a whole sentence can be embedded. So if you imagine sentence A, I enjoy machine learning. Sentence B is I like studying AI. Although the words differ, the meanings are similar, right? So their sentence vectors become nearby points in embedding space. So if you embed these two sentences, though they on the face value they may look like they are not close, but in human language we know they mean about the same thing. So, and then we go on, that's the idea of sentence embedded. So we can embed whole sentences instead of just tokens or words. Then we have semantic search, right? Traditional search relies on keyword matching. So, keyword matching. Imagine a query, car repair. So and you have a document, automobile maintenance guide. So keyword search may miss the match because no words are identical. So car and repair, and then you have automobile maintenance guide. So you don't have car here, you don't have repair here. Neither do you have automobile maintenance guide in this other one. But then, of course, as humans, we know that they have things in common. So keyword search may miss the match because no words are identical, but semantic search solves this problem. So the query and documents are converted into embeddings. How close are they in general human language, right? So because car is almost like automobile and repair is like maintenance, their vectors become similar. So the documents can therefore be retrieved even without exact keyword overlap. So the semantic pipeline then becomes something like this: the user query, then embedding model. So what model are you what model embedding model are you using? Are you embedding tokens or words or even sentences? Then you have the query vector. So and then you have the similarity search. So you now have a comparison between between your query and your documents, and then from there you get nearest documents. So, we move on. Imagine a semantic search example. Suppose a query embedding is this. Maybe you put your query and it is embedded to be 0.8, 0.9 based on how they exist and the context. And then you have documents D1, D2, D3 with 0.75, 0.95 minus 0.7, 0.2, D3, 0.8 to 0.88. Now you'll see that of all of these things, the closest to Q here is D3 because this is 0.8, this is 0.82, this is 0.88, this is 0.9. So the distance, even the face value distance is like 0.2 in each case. So this one may look close, but this is definitely close up. This is totally far away, right? So if you compute cosine similarity between the query and every document, so you find cosine similarity between this query and document one, query document two, query document three. So the most similar documents are returned to the user, and that's where you get your prompt. So in this case now, imagine the query itself is 0.8, 0.9, and you have your documents. Cats make wonderful pets, 0.75, 0.95, truck engine repair minus 0.7, dog training guide is 0.8, 0.88. So you have for dog in vec, for dog in vec, in docs items, then you want to find the similarity by doing the dot products for q with the vec. So this docs has been defined as vec, right? So you do that and you do the cosine similarity. This formula for cosine similarity, right? So if you do that, and you run it, so you see cat make wonderful pest is 0.998, and then truck engine minus 0.433, dog training guide. So 1.0, that's like perfect. So like I said, this and this are like perfectly in the same direction, followed by this other one, 0.998. So you see the expected outputs now. So cats make wonderful pets, 0.998. Truck engine repair minus 0.35, then far away. Dog training guide 1.00. So the ranking is that the dog training guide is number one. Then cats make wonderful pets number two. Truck engine repair number three. So it means that the query that whose embedding is 0.8, 0.9 is mostly aligned with document three, where you have the idea of dog training guide. So the results align with human intuition for sure. Now, let's talk about retrieval systems. Modern retrieval systems use embeddings extensively. Examples include search engines, question answering systems, recommendation systems, chatbots, retrieval augmented generation, and enterprise search. So imagine search engines, right? Google and all any search engine you can think about. Then question answering systems, recommendation systems, and all of that. So they use embeddings extensively. So this objective is simple. The objective is simple. Given a query vector, find the nearest document vectors. That's basically what retrieval systems are about. So if you put a query, so you want to see where can we easily get the answer to this query, basically. So imagine the retrieval pipeline as this. You have at the offline stage, now you have the documents, you have the embedding model, you have the document vectors, and you have your vector database. Then so this is like maybe what is already in your AI model or so. Then for the query stage now you have your user query, the embedding model for your user query, the query vector even the vector for your own query, then the nearest neighbor search. So you're searching for documents that are close enough from the vector database, and then you then get the top K documents, you know. Now the question now is why vector databases exist. Why do vector databases exist? So you see vector database somewhere around here. So why they exist? Suppose you have a collection which contains 10 million documents. Okay, you have a collection containing 10 million documents. So computing similarity against every document could would be would be expensive for sure. So vector databases store embeddings efficiently and support fast nearest neighbor search. So nearest neighbor search is a kind of supervised learning algorithm in machine learning. So popular systems then include FAISS, Milvus, Weaviate, Quadrant, and these systems make semantic retrieval practical at large scale like that. So vector databases store, they store embeddings efficiently, and they can help to do quick search. Now, the question again comes: why similar words live near each other? Why this? This video is about, right? The complete explanation then is this: that vectors are represented as words are represented as vectors because humans understand words. Machines do not understand words. Machines understand numbers, and numbers can be represented as vectors, right? So then, when human words are represented as machine vectors, so to speak, then the vectors are learned from context by the machine. Then similar words appear in similar context, then learning algorithm push similar context words towards similar representations because they look at the occurrence of words in documents, in text, tons of text, that is. Then similar vectors occupy nearby regions of space, and similarity can be measured using cosine similarity. So retrieval systems exploit this geometry to find relevant information. So the central insight is this: meaning becomes geometry. All right. So you have words, you have sentences and documents with similar meanings occupying nearby locations in vector space. So that is a summary of what we've been talking about. So key takeaways again: distributional hypothesis, words appearing in similar contexts tend to have similar meanings. Settled. Then for vector representation, now words are represented as vectors. All right. So you have W sub I of R in D-dimensional real number system where D may be hundreds of thousands. So you can have hundreds of thousands, just like we said right from the first video. So AI is just some simple mathematics done on tons of data, and then it becomes something out of this world, if you like. Then talking about similarity, the most common similarity measure, which is preferred to Euclidean distance, is the cosine similarity, which is dot product over product of magnitude of two of the vectors involved. Then for applications now, of course, we have this applied in things like semantic search, information retrieval, the RAG systems, recommended systems, question answering, large language models. The entire modern embedding ecosystem is built on the idea that semantic similarity rather corresponds to geometric proximity in vector space. So words become vectors, word to vec. That's the kind of idea. So we come to our practice problems. As usual, we have 20 of them. So here you can see the first five clearly, first five questions clearly. As usual, I get to solve two of them to drive the point home as much as possible. So in this case, I'm going to be solving problem two, which says suppose the embedding vectors are A, 3, 4, B, 6, 8. Compute the cosine similarity. Of course, you can already see that the cosine similarity is going to be, this is just a product of this. So they are in the same direction. You can already know it is one because I mean, if you can factor out a number here and get the same thing, so the similarity is going to be one. So I'm going to take care of this question two. Then, okay, so you can see questions to you can see 6 to 11 here. Question 6 to 11, you can see them here. Then, uh, questions 12 to okay, let's say 12 to 16 for this. You can see question 12 to 16 completely. Then you have question 17 to 20, or okay, yeah, question so maybe you can still see 16 to 20. So again, I'm going to take care of question 20. Design a simple semantic search pipeline by listing the major steps from user query to ranked document results, including embedding, similarity computation, and retrieval. So we're going to talk about that a little bit. And then this video will be over. So let's go for that. Um, let's go for that on the uh worksheet page. So I guess I have to let this go. Um, okay. Yeah. So Now, problem two, given A equals 3, 4 and B equals 6, 8. In fact, if you are doing multi-choice question, once you see that this is a one is a multiple of the other, just know that they are in the same direction perfectly. So you don't even waste your time. Just know that they are in the same direction because the answer is going to be 1. So we are asked to compute the cosine similarity. Cosine similarity. Okay, all you just need to do is this. Step one, complete. Of course, first you get the formula, right? You know that similarity, let's just say cosine similarity. Cosine similarity is equal to the dot product of the vectors all over the product of the magnitude of the vectors. So that's the idea of cosine similarity. So we already have our AB, right? So 3, 4, 6, 8. So we can just go straight. This is 3, 4 dot 6, 8. Like that. All over magnitude of 3, 4 multiplied by magnitude of 6, 8. Like that. So if you to implement that, you just have um that's 3 times 6 component by component plus 4 times 8 divided by, then the magnitude here is square root of 3 squared plus 4 squared. So the square root of 6 squared plus 8 squared. So that's cosine similarity. Let me just call that CS. CS there. So you have CS, 3 times 6 is 18, 4 plus 4 times 8 is 32, divided by square root of 3 squared plus 4 squared, that's 25 there. Here, 6 squared plus 8 squared, that's 100. That's 100, yeah? So cosine similarity now, cosine similarity, which is CS still if you like, is equal to 18 plus 30, that's 50, divided by square root of 2500. Okay, and that is 50 over 50, and 50 over 50 is simply 1. So that tells us that okay, so therefore the vectors point in exactly the same direction. The same direction, and are therefore are therefore maximally similar. Okay? Maximally similar. So any words represented by those vectors are actually words that are similar, maximally similar. So they live close together. Okay, so now we move on to question 20. Yeah, problem 20 now. Problem 20. So here, want to design a semantic search pipeline, a semantic search pipeline from user user query to ranked results. That's the deal. To ranked results. So we saw the procedure in the process of explaining, right? So step one, you have user enters a query, right? So let's say the user enters a query. So let me just go like user query. So you have user query like how do I improve how do I improve laptop battery life? Laptop battery life. So that's a query, put into an AI model, so to speak. Now, that's step one, right? Step two, uh, convert query to embedding. So query into embedding, right? So the query is converted into an embedding. So that's something like this now. So the query is now, maybe the whole sentence is embedded as 0.42 minus 0.18, 0.91, and so on and so forth. Okay, so we have that. So here, the vector captures. Of course, the machine does that. It's not humans that do this. But of course, you can do that as a human too. But if you have tons of data, it doesn't make sense for you to sit down and start ranking sentences one after the other. Like, yeah, imagine you have 1 million sentences. So the algorithm, whatever algorithm you're using, will do this. So the vector captures the semantic meaning of the query. Okay, then we go for step three now. So step three is documents are already embedded, right? So before search begins, every document in the collection has been converted into a vector. So next stage is about, checking embedded documents. Embedded documents. Let's say we have documents. We have the first document that's for extending, tips for extending notebook notebook battery duration. Notebook battery duration. Okay. So that's the that's D1 right there. And that is embedded as 0.40 minus 0.20, 0.89, and all the rest of them like that. So that's D1 there. And then maybe we also have D2. D2 now is how to repair a laptop screen. How to repair a laptop screen. That's another document. Okay. So we have this also. And then the embedding is something like D2 equals minus 0.31, 0.55, minus 0.12, and so on and so forth. Then we have a third document, say D3, which is now smartphone charging guide. Smartphone charging guide. Okay. So you have D3, which is 0.15, minus 0.40, 0.33, and so on and so forth. So that is the embedding for the third document. Now we go for the fourth step now. So for the fourth step, step 4 now, it's about computing similarity scores, computing similarity scores, scores. So the system computes cosine similarity between the query vector and every document. And that's like you have similarity of the query and every document, which is q dot d sub I all over the modulus, the magnitude of q and the magnitude of each document di. So in that case, let's say we have example scores now. Example scores. You then have you have your document and the document, and you have cosine similarity. Cosine similarity. So that's not like D1, 0.96, D2, 0.42. That is the similarity between the query and D1 is this. So don't forget the D1 is the query itself is how do I improve laptop battery life? So here, tips for extending notebook battery duration. Yeah. How to repair laptop screen, smartphone charging guide. So, but the closest is 0.96 because D3 now is 0.58. So with that in place now, you can rank the documents. I mean, it's already ranked. 0.96 is closest, shows D1 and the query are the most similar. And then we go on to rank documents now. You rank the documents. Of course, the scores are clear about the ranking. Of course, maybe you have 10,000 documents, so it's hard to see all of them, but the computer does all of this. So sort document by similarity score, right? So um So we sort the document by similarity score. So if we sort by similarity score, right, it means that from here now, this is number one, this is number two, this is number three. Okay. So that means that we have D1 is number one, and then so D1 is one, then D2, D3 is number two, then D2 is number three based on the similarity scores. So next then you have top return, and you then return top K results. So the search engine returns the highest ranked documents. So uh the example here is number one, tips for extending tips for extending notebook notebook battery duration. Okay. That's that. Number two, smartphone charging guide. Smartphone charging guide. And three, how to repair a laptop screen. So we can then have the complete pipeline, right? Complete pipeline. So the complete pipeline can then be something like you have your user query, first step. Then you have the, okay, let me go like this, embedding. Okay, maybe that doesn't work well. So you have the embedding model. Then you have the query vector, the query vector. So once it's embedded, you can turn that into a vector. Have the query vector, and then okay, from the query vector, so all the vectors are then stored into a vector database, for easy usage, vector database. And then from there, can calculate cosine similarity computation. So you can do cosine similarity computation. So the query compared to each document, computation, computation. Then from the computation, you can do the ranking based on the similarity scores. And finally, you decide for the top K documents returned. So, and with that in place, so we see that the key idea is that semantic search retrieves documents based on meaning rather than exact keyword overlap. So even if the words do not look alike, so the semantic meanings, which is made possible by the embeddings. All right. So for example, laptop battery life can successfully retrieve notebook battery duration because their embeddings are close in vector space. So with this, we come to the end of this interesting video about why similar words live together. So again, I'll show you the questions to try your hands on. So you have the practice problems. You can see 1 to 5 here. Then you can see 1 to 6. I mean, say 6 to 12, right? You can see 6 to 12 here. Then, okay, 6 to 12. Then you have 13 to 18. I mean, 13 to 17. And then you can see the rest. So with this, let me know. We've come to the end of this interesting video. Let me know how helpful this is for you. And there's something that you like on the try out, feel very free to let me know. If you have subscribed to this channel already, thank you very much for doing that. And if you have not subscribed, what exactly are you waiting for? Why not go ahead right now and subscribe to the channel and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges to find out when you click on join. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.